So I don't have a good voice today, so please, I feel sorry, but it is what it is. If I cannot continue to teach, maybe I will finish earlier. So we'll see. So for today, let me start recording. So I'm supposed to introduce genetic algorithm. Last time, some of the groups already introduced GA, so I feel very thankful because you already covered some of the information for GA. So today I'm going to help you understand more about GA. GA is a very simple method, everyone can use it. The concept is, when do we use GA? Usually when you cannot take derivatives. So in my opinion, there are two situations that you can use GA. One is you cannot take derivatives. Meaning, one example, if you say your x must be integer in a range from, for example, from 0 to 100. In that case, there's no 1.2, 3.5, they are integers. So when you try to use finite difference to compute the derivatives, for example, if you want to evaluate partial f, partial x, at, for example, at x equals to 1.2. So usually what you do is 1.2 plus your delta minus 1.2 divided by delta, right? Or if you want to do this, at x equals to 1. In this case, 1 plus delta minus f of 1 divided by delta. Maybe at 1 plus delta is not available. Because let's say your x is the number of people. So I'm solving an optimization problem with decision of human head counts. I need to decide, okay, how many workers I should send to a factory so I can optimize my efficiency. There's no 1.5 people. So that kind of evaluation is not available. So in this kind of math problems, you don't even, you cannot even take derivatives, no derivatives. Then it's really difficult for you to use gradient-based approach anymore. You cannot use gradient-based approach. Another situation is if you are looking for global optimal. If your problem is very nonlinear, it has many local minima. For gradient-based approach, if this is your objective function, if you use gradient-based approach, let's say your initial guess is here. The gradient will lead you to a local minimum right here, but it doesn't guarantee the optimal is global. Okay? So how come GA has the ability to find global? Because it introduces some kind of randomness to the process. So that kind of randomness allows the design point to jump around inside the design space. Later on, I will try to show you how the solution points are jumping around inside the space. And if you're lucky enough, some of the solution points may get closer to the global optimum. So GA has the ability to find global optimum. So GA is not the general terminology or general name for methods like this. Actually, there is another name. It's more that could represent all kinds of methods like this. So they are called the evolutionary optimization methods. So GA is one of them. Okay? So the way when they use evolutionary is because they usually try to learn from the nature and see how nature evolved from one kind of species or object and evolved to something different. And some people try to use math to describe that kind of evolution. So they use that kind of concept in optimization process. They hope this kind of random process will give you the ability to find global optimum. Okay? So I will give you one example. If you are solving this, and for example, x1 and x2 has to be positive. And hold on, let me use it different. X1 is within, for example, 100, okay? And the other one also 100. So there's in the design space, there's a box. Here's x1, here's x2. So here's 0, 0, here's 100, 100, okay? So the solution set is inside the box. And also x1 and x2, they are integer, okay? They have to be integers. That means how many solutions are there? 101 times 101. Okay? Solutions. Okay. So what you can do is you can try all of it. But if you have even greater scale, even greater size of the design space, then sometimes it's very difficult for you to try everything. Okay. So the goal of GA is to try to solve the problem without testing all of it. Later on, I will formulate this into a certain way. So all the possible solutions, the number of all the possible solutions is quite large. So if you want to examine every one of them, it takes a lot of time. So in this case, it's not yet a super large problem. So 101 times 101 is 10,201, right? So we can try 10,201 positions, and there is the best one, of course. Let me try to put a constraint function here. So let me say something like about a nonlinear one. Maybe something like this. Something like this. So I know this is a function like I may need to make a plot to figure out what is a good number of it. I need to find a good function. Okay, so it has to be very small. Okay, so I think this one is okay. Maybe slightly larger. Okay, yeah, I like this one. So, back to iPad. The function looks like, give me a second. Okay. Yeah, so the function looks like this. Okay? It's a quadratic function like a curve, and anything above it is good, underneath is not good. So my solution would be somewhere maybe here, right? Because the objective function contour looks like this, right? So somewhere at the middle is the optimum. Okay? Now, but for easier implementation, let me see. I want to get rid of this line. I don't want to force them to be integer, okay? Because later on I need to show you how it looks like. But so over here, let's say we cannot take derivatives. Okay? For some reason you just can't. So all the methods that we have learned requires derivatives. Right now, if we cannot take derivatives, how can we solve this problem? Even though it doesn't look so difficult, but without derivatives, we really don't know what to do. So in evolutionary optimization, especially in GA, they will try to randomly choose their design point. Okay? So now I'm going to convert the decision of x1 and x2 into binary. Okay, binary. So first step, binarization of variables, or all the decisions that you need to make inside the optimization problem. So in my case, I'm gonna, let me see what I'm going to do. So if I 2 to the power of 5, 6, 7. Okay, how about I'm gonna cut the range from 0 to 100 into 1,000 small digits, cut small pieces. So I will use 10 digits, so 10 of them. This is 10 digits to represent x1. Okay? So they are binary, so they are 0 or 1. So they are 0 or 1. Okay? So in this case, ten zeros is gonna be 0. Okay? How about the largest one? You know, for 10 digits, you have 1,024 possible combinations, right? Combinations. So the last one would be all the ones. And 10 ones, if you convert it to decimal, I believe it's no, actually I only need 9 of them. 9 of them. Then I can cut into 1,000 combinations. So just 9 of them. 9 digits. And because 2 to the power of 10 is 1024, right? And one digit, so what is 2 to the power of 10 is going to be 1, 0, and 9 zeros, right? This is a binary. This equals to 1024, right? So 9 ones is going to be, if there are 9 ones, it's 1023, I believe. Am I right? 2 to the power of 9. Just to double check. Do I need 10 or 9? I think I need 10 digits. Because the last one plus 2 to the power of binary. This is how many? 8, 9, 10. Okay. Okay. So I need 10 of them. I was right. Sorry. I need 10 digits. 10 digits. So 10 ones. 10 ones. This is 1023. Yeah. 10 digits. So D. Okay. So 10 ones is 1023. So totally I have 1024 combinations. So for the value, how do I use this binary code to represent the value for x? So your x is gonna equal is going to be because it's ranging from 0 to 100. So so the yeah. Did I make a mistake?
No.
Didn't switch. Sorry, I'm sorry. Yeah. So the value for your x1 equals to the binary code, and then divided by 1023 times 100, is it? Because if it's a 1023, then it's 100. If it's 0, then it's 0. Is it right? That should be right. So you can use this to represent some value from 0 to 100. And you basically cut into 1024. 1023 pieces, and you can represent 1024 different values. Okay, so do the same for x2. So at the end, I will have, this is 10 digits. I will have 20 digits to represent all the possible points inside the design space. So I would totally 20 digits. So if I have 20 digits, how many possible solutions? 2 to the power of 20 possible solutions. So what is 2 to the power of 20? It's 1 million. 1 million solutions. If you really want to test all the possible solutions, you can, but you need to try it 1 million times. So the goal of GA is to use fewer amount of possible solutions and try to find the optimal without testing all 1 million possible combinations. Okay, so since we have a long digit of 0 or 1, first half represent the value of x1, the other half represent the value of x2. This whole thing is like a DNA DNA code. So we call this chromosome. Chromosome. So for Taiwanese, this is 染色体. For Taiwanese, if I tell you the Chinese, you know. But for foreigners, chromosome is a string of ATCG inside the DNA. It's called a chromosome. So basically, a string of DNA codes in our body or any species is called a chromosome. Okay, so we use the name because we are treating this math problem as a evolutionary process. So this is basically the 20 digits of 0 or 1. Okay? And we are going to randomly generate different chromosomes out of all the 1 million possible combinations. We're going to randomly generate those and see if we are lucky enough to find the optimal. So, there is actually standard procedure of GA, but in my opinion, you don't really need to follow exactly the procedure. So I'm going to tell you some of the very common procedures. So in GA, we don't call iteration anymore. So in GA, they rename iteration as generation. Okay. So in different generation, you have new species with mutated chromosomes. So they just put this evolutionary procedure into the entire mathematical problem. So they don't call iteration anymore, they call generation. So in each generation, basically each iteration, you need random species with certain amount of random chromosomes. They call this amount of basically randomly generated chromosomes. up to a certain amount. So we call this like a number of chromosomes. Chromosomes. No, actually we don't call it number of chromosomes. We call it basically population. The amount of chromosomes. We just directly call it population. So let's say in my problem, let's say I'm gonna produce this kind of random generation for 100 times, for example, 100 generations. And in each generation, I'm gonna randomly generate 20 chromosomes. So my population for each generation is gonna be 20. So that means in total, I will be testing 2,000 chromosomes for the entire generation GA process. I'm only going to test 200 chromosomes, 200 different chromosomes, 2,000 different chromosomes. So out of 1,000,000 possible solutions, I'm going to test 2,000 only. So I didn't explore the entire design space. I'm relying on a much smaller amount of solution set. And hopefully I can find the global optimum out of this many chromosomes that I randomly generate. Okay? So each generation I randomly generate 20. So you will be moving on to the next one and the next one and the next one. Every time you will be generating around 20 chromosomes. Okay, so up to now you may feel weird. How come this is going to work? The possible solution is 1,000,000, but you are only testing out 2,000 of them. How is this possible? Okay, so it's fine. This is how the algorithm works, and so you need to bear with me. And at the end, I can use a meta code to show you how it's gonna work. So every time you randomly generate this chromosome, you need to check how good the solution is. So usually, for a problem that I have one constraint function right here. Okay? So the way I define the binary digits automatically will make sure I satisfy the variable bounds, upper bound and lower bound. So I don't need to worry about the first two constraints anymore, because the way I design it, my solutions are just inside the boundary. Don't worry about getting out of something, getting something outside of the variable bound. But during the random generation process, it's very possible I can generate a point that doesn't satisfy the yellow constraint. So now you need to decide, what would you do if you see some random chromosome that doesn't satisfy the yellow? So what's gonna happen is, usually there's a procedure so-called a feasibility check. So if you randomly generate some chromosomes in one generation, there must be some chromosomes that doesn't even satisfy your constraint. You need to decide, do you get rid of that one or not? Okay? So in my case, I'm going to just delete the ones that is not feasible. So if I randomly generate 20 of them, I need to check, are they all feasible solutions? If one of them is not feasible, I will kill that chromosome, and I will generate another one. So I want to have 20 feasible chromosomes all the time. That's my choice. Do you use the same procedure? It's really up to you. I have seen papers, when they have feasible points, they still keep it. Because sometimes the infeasible chromosome maybe have some good genes inside. So all they do probably, they can so-called penalize. They can penalize that chromosome. Give the bad chromosome a poor score. But there is still a possibility that poor chromosome can contribute in the future. Okay, so I will tell you about the score later on. So here you need to make a decision. What do you do for infeasible ones? So over here, if infeasible, in my case, I will delete and randomly generate another one. So I will keep on doing this until I have 20 feasible chromosomes. Okay? Once you are done with the feasibility check, you will move on to, so this is like a one standard procedure. In my case, this is one procedure. So once everything is done, I will move on to a next procedure. So next, it's so-called, we need to check so-called fitness value. So what is fitness value? You need to define your own fitness value. How fit the chromosome is. If you are not able to define how fit your chromosome is, you cannot continue GA. So basically, it's like giving a score to the design. Giving a score to the design and evaluate how good it is. Okay? So in our case, we are minimizing objective function, right? So if I have a bunch of randomly generated chromosomes, then they are all feasible, because during the feasibility check, if it's a bad one, I kill it. Now I should have 20 good ones. They are feasible points. And I will check the objective function for all designs. If the objective function is small, it's a good one. So over here, I'm going to use my objective function to determine how good my design is. So in my case, my objective function value is the fitness value. Okay? And in this particular example, smaller the better. Okay? So does fitness has to be larger the better or smaller the better? It's really depending on how you program the code. So in my case, I can treat it as a smaller the better. Now, so the next step is called a selection. So it's like all of you are chromosomes, feasible chromosomes already. I give everyone a test. I evaluate every one of you based on some kind of score. Okay, this person has a good score. Okay, he's a good one. He's a good chromosome.
I want to have more of this good chromosome, and maybe another chromosome which is bad. Okay, give me less of it. Yeah. So in the selection, there are so many ways to select out of the available chromosomes. They even double select the good ones. Why do they do that? They want the good chromosomes to have greater probability to be chosen. They believe a good chromosome with good fitness value has greater opportunity to contribute for finding the other. Because out of the current chromosome, some chromosome is good, some others are bad. So it must means the good ones, basically, every chromosome is composed of 20 zeros and ones, right? So the good ones basically is a combination of 0 and 1s, the 20 digits. So if it's good, maybe it's because some part of the chromosome is already the same as the true solution. So they want to keep it because this chromosome is good, has a greater opportunity to become even better. So the selection process, last time when one of the group presented this, they introduced Russian roulette or some probability based selection procedure. Basically the goal is to have more good ones, fewer bad ones. So what I'm going to do, I don't remember the name. Maybe it's actually Russian roulette. So the idea is I'm going to generate a circular target with different, like a pie chart, okay, like a pie chart. But this is only conceptual. In computer programs, you don't really need to draw a circle. So I have a pie chart. So every chromosome will be placed inside this pie. So for example, this is my best chromosome. Okay? So how come this best chromosome has a wider range? Because its fitness value is the greatest. So I will mathematically define how wide it is. So maybe the angle is determined by how good it is. So one of the way is to compare the fitness value of all the chromosomes. So maybe because this one has the smallest, so I can if I give if the fitness value is called for example, I don't want to use F anymore. If I use capital F, okay. So capital Fi represent the fitness of ith chromosome, okay. So after evaluation, I will have a mean best one and the worst one, right? I will have a mean. Mean is basically the best for current generation, right? So this will be the worst. So I need to come up a way to decide the like a percentage percentage of the best chromosome. Okay? So maybe what you can do is you can have a sum of them. But right now, smaller the better. So maybe if I use inverse, it will be better. Okay, so maybe I will compute F max minus Fi. I will compute a value like this. So for the best one, for F mean, if I call this value D, if I call this Di, okay? So for the chromosome that has the best one, for F mean, Di is the largest, right? So for the worst one, basically Di is 0. So you can, this is one way for you to generate some number. Now is larger the better. So Di is larger. If you are better chromosome, your Di is larger. So at the end, this percentage can be formulated as Di over sum of D. And because every chromosome now has a Di, now the best one has a greater D, right? And you want to multiply by, for example, 100%. So there is a chromosome has the best fitness value. It will have a largest Di. So if you use this to evaluate a number, it's gonna be a percentage. So I'm gonna use this value to represent the probability this chromosome to be chosen in the next round. So if it's a good chromosome, it has greater percentage to be chosen. Okay? So it's a probabilistic approach, and the approach tries its best to choose the best one multiple times. So next, you will select 20 of them, 20 chromosomes. Based on this probabilistic selection. And because the best one has greater percentage, it's possible the best one to be chosen twice. It's okay. If the same chromosome is being chosen twice, that's totally fine. Okay? So once you're done, you will have 20 newer chromosomes. Maybe some of them are duplicated. They are the better ones. And there are some others are not even being chosen because they are pretty bad. Okay? So now you have 20 of them. Then you are going to perform something called crossover or mutation. Okay. Which one goes first? Either way. So what does crossover do and what does mutation do? In crossover, Basically, you are going to select 2 chromosomes out of the 20. So you will have 2 of them. They are all 20 digits. And you're going to choose a random, you're going to use a random number generator. So, and you will have a pointer. This is a pointer. Okay. So the pointer is gonna move digit by digit. Every time when it moves by a digit, you are going to randomly generate a number. Basically, from 0 to 1. So let's say you generate a value, say 0.3. Okay? So if the random number is, for example, larger than some so-called crossover rate. Actually smaller than. If that happens, then perform crossover. Okay? So what does crossover do? So for the 2 chromosomes, let's say when the pointer moves to somewhere here, and the random number now is, for example, 0.3, and if your crossover rate is 0.35, that means 35% probability you will do crossover. So at some point, when your pointer moves to somewhere, and you randomly generate a number that is smaller than the crossover rate, okay, now perform crossover. So what does crossover do? Crossover directly swap some part of the chromosome. They swap their body. Sometimes it's so-called a one-point crossover. That means just define a single point, the rest of the body perform swapping. Sometimes it's called a 2-point crossover. So they randomly generate 2 positions, maybe the middle part, swapping. Why do they want to do this swapping? And why do they don't want this kind of ratio to be low? They don't want this ratio to be too high? Because think of the chromosome. It's basically a string of 0 and 1. The optimal solution is also a string of 0 and 1. Maybe when you have a good chromosome, which is close to the optimal, maybe some of the digit is already the same as the optimal. But some other digits are not. So they want to generate some kind of random process allowing a chromosome to change the value. If they are lucky, they can get all the good genes together. So this is how, and that's why they want to keep the good ones. They want many good ones, but they know the good ones is not yet the best. So they still need some genes from some other chromosome. They use this kind of swapping procedure. If you are lucky enough, maybe the other one has some other good genes can be swapped to this one. Okay, so this is so-called a crossover. For mutation, usually only works on one chromosome, and the pointer points at the digits. Similarly, you randomly decide which chromosome to be mutated. I should say which digit to be mutated. Mutated. So what does mutation do? If the digit is 0, then becomes 1. If it's 1, then becomes 0. Okay? And usually the mutation rate has to be low. So usually mutation rate is lower than crossover rate. Okay? So once you perform crossover mutation, at the end you will have a bunch of mutated chromosomes, new chromosomes. So you will have new chromosomes. You will check fitness again, and you are moving on to the next generation. So usually they will keep the best one. So keep, we call that elite chromosome. You can keep 1, you can keep 2.
So you say it should be lower, but how much is lower?
So it's really up to you. So you can read papers. Okay, oh, they solved this problem. They choose the mutation rate to be 5%. Okay, I try it. Sometimes, if your crossover rate and mutation rate are too low, then there is not enough randomness. If the randomness is not enough, then the solution process will not explore the design space randomly enough. But if your mutation rate and crossover rate are too high, too much randomness, you will see your solution point is jumping around inside the design space. So it's really difficult to say what kind of ratio is the best. So usually check some papers. If some papers solve similar problems, they will tell you what are the crossover rate and mutation rate they use. You can start from there. And then you need to observe your design solution process and make a decision. Do you want to change the rate? Later on, I will program and let you know. So at the end, you will pick up the elite, the best, overall best chromosome. You can keep 1, you can keep 2. And then you move back. Go to next generation. But when you go to generation, you keep the elite chromosome, the overall best. So starting from the next generation, you still have the best ones from the earlier generation. You will generate more chromosomes. So if I keep 1, so I will generate 19 new chromosomes and continue. So you will not lose the best one. The elite chromosome stays there all the time. And you need to, then you will rely on this random process and hope eventually you can find the overall population. Okay, so now let's go to MATLAB and see how it's gonna look like. Okay, so I will need some kind of binary to decimal. Okay, so binary to decimal, let me double check. Okay, by strings. So initially, this is a generation, right? You will be, I need some basic setting. Population equals to, I said 20. And generation, I said 100. And let's say crossover rate, let's say is 30%, mutation rate, let's say it's 5%. Okay. Now, for I equals to 1 to your population number, you want to generate 20 of them, right? And you are going to randomly generate 20 0 ones. So let me figure out a good way to formulate this. So I'm gonna call my chromosomes. Maybe I just call them X. Or yeah, X. So my K equals to 1. K is going to be my generation number. So it's like an iteration number. Okay. Let me just double check some. Just double check. If I have a vector of 0 and 1, and if I convert to string, that would be, can I convert to binary to decimal number to strings? Oh yes, okay. So I will have just random. If you use rand is uniformly distributed random generator, and I'm gonna generate. Do I generate a horizontal one? Yeah, horizontal 0 and 1s. So 20 and 1. Okay? So if I uniformly generate 0 and 1, they are values from 0 to 1. Then if I use round, if I do rounding, they will either become 0 or 1. Okay? Just show you. If I do that, they will be a bunch of 1 by 20. I want it to be horizontal. So 1 by 20. So by this, I can generate a horizontal vector of 0 and 1 that's just randomly being generated. Okay, so I'm gonna call this one K and if I have K and I, maybe I will have a cell X I. This curved bracket is for cell. So K, curved bracket K, and then I comma column. So I will have 20 of them. right? And they are horizontal vectors. But every time when I generate, I need to be sure they are feasible. So I'm going to do feasibility check here. So in order to check whether this design is feasible, I need to convert them back to the x1 and x2. So over here, I'm gonna do feasibility check. Okay. So over here, the first half and the second half will be converted back to x separately. So k and 1 to 10, comma, column. This is the first half. And 11 to the last one. This will be my second half of the chromosome. So I need to convert, basically it's a string of 0 and 1. I will have number to string. So it will become string, basically characters. Then I need to say decimal, binary to decimal. Okay, binary to decimal. So that will convert the value to 0, from 0 to 1023. So now they are values from 0 to 1023. I need to divide this by 1023 times 100. Then they becomes values ranging from 0 to 100, just like what I show you in my problem. So now here it will be my x1 value. This will be my x2 value. Okay? So once I have them, I just need to plug into the constraint, see if I satisfy the constraint. So if x2 value is smaller than 0.01 times x1 value minus 105 squared. If this is happening, that means not feasible, right? Then I need to generate another one. So over here, I need a while loop. I need to keep on generating until I find a good one. So over here, I'm going to generate a flag. It's called a feasible flag. At the beginning, it's 0. So while feasible flag is 0, I will do this. If it's not feasible, then actually, if it's feasible, larger than or equals to, if it's feasible, then you can convert the flag to 1. Right? If it's feasible, then the flag equals to 1. And this while loop, once you see the flag equals to 1, when you go back to here, okay, it's feasible already. Then the while loop finishes. So it will go back and generate another chromosome. Okay? So let's take a look. I'm gonna do something for the plotting. So x is equal, and x limit 0 and 100, y limit not x limit right limit 0 and 100. And then I say hold on. So whenever I generate a feasible point, I will draw where the point is. So I'm gonna say plot x1v, x2v, and then I just draw a small dot, maybe in the red color, and marker size probably just 5. Okay, and let's run the code. Something is wrong. Double check why. Run the code again. So this is the problem, right? We are looking for some position on the upper right corner where the objective function is the smallest. Over here, I'm not sure, let me see what's wrong. Let me see. Mistake. It should be the ith one and then 1 to 10. Ith one, 11 to the end. Okay? That's it. Okay? So, let's take a look. Did you see 20 dots on the upper right corner? There's no dot on the left lower corner. Because whenever it's not feasible, that one won't be, my while loop will not keep that chromosome. So now I randomly generate 20 dots on the upper right corner. Any questions? Did you see what's going on? Over here, random process to generate 20 0 and 1s, 20 random numbers from 0 to 1. Use rounding, they become 0 and 1. So 20 0 and 1s. Convert to decimal, or convert to string. So they are 20 0 and 1s, but they are characters. Now binary to decimal, converting to a real number. So it will become an integer from 0 to 1023. So 0 to 1023, if you divide it by 1023 times 100, it becomes a value ranging from 0 to 100. My design space ranges from 0 to 100. So by doing so, doing this twice, I have x1 and x2. And I just, over here, this is my constraint. If satisfying, then I convert the flag from 0 to 1. So the while loop will not continue again. Maybe we can take a look at the flag, okay? So maybe we can stop right here. Run the code again. So over here, this is I equals 1. So in this particular trial, we bump into 74 and 11. 74 and 11. 74 is somewhere here, 11. So it's some point infeasible, okay? So my feasible flag was 0. Because it satisfied the flag equals to 1, plot out the point. So you can see it's within the feasible space. Upper right corner is the feasible space. And when you go back to the while loop, it doesn't continue a second random generation because that one was a good one. Okay? So it will continue for this process at the end. That's why we have 20 of them. And you can see from the first trial and the second trial, the 20 random points are located at different positions. So every GA process should be a little different. Actually, it's largely different. Okay, it's a process that relies on randomness. Okay, now we have the chromosomes, 20 of them. I need to check their fitness, okay? So I'm gonna check the fitness just here, inside the loop. Because once I know it's a good one, I'm gonna check its fitness. So I am going to just say fit, and then bracket k comma I. Okay? So my fitness, I just need to plug in my objective function. So it will be square plus 10 times x2 value squared. So I'm using this as my fitness. I know the smaller the better. I know the smaller the better. Later on, because I need to do selection, so I am going to use what I said. After I generate 20 of them, I need to see which one has the largest fitness, which one has the smallest. So the fit max equals to max of all the fitness values, and fit main is the smallest. Okay? Once I have the largest and the smallest, I'm gonna create the value so-called the D. I'm gonna use it to decide the percentage of one chromosome to be chosen. Okay? So D is going to be a vector. It's gonna be fitness of max minus all the fitness for this particular chromosome. Okay? I'm gonna show you what's going on. Okay, so now the fitness, if you take a look at the fit, they are 20 fitness values. Some of them are quite large. And the minimum one is this one. The maximum one is this one. So how about the D? D would be, because I use the largest fitness minus the each fitness value. So now the best design will have the largest D. Okay? So I'm gonna use D. So the selection percentage, I'm gonna call this percentage. Okay? Equals to D divided by the sum of D. Okay, so if I do this, what's the percentage? So they are, if I show you, percentage. Okay. So let's see if there's a chromosome that has the greatest percentage. Or maybe I sort percentage. So there's one that has 0%. Okay? And there are some other bad ones, they even have a percentage that is smaller than 1%. What is the largest one? The best one has 9% to be chosen. We have 20 of them. So without fitness, originally each one of them has maybe 5% to be chosen because you have 20 of them. they were, before fitness check, they were equally, they are equal. They are just randomly being generated. But now, after I check the fitness, I like the good ones. So I want to increase the ones with the best fitness value. So there's even some chromosomes has percent 9% to be selected. Okay? So now what we do, we are going to, so this is just like the pie chart that I showed. So each chromosome had occupy a percentage. So I'm going to randomly select out of this percentage, and we're going to use this random process to pick up and see if the best one is being chosen. So what do we do? Now each okay, I think I should sort. So if I sort, but I'm sorting along the descending order. So the largest one goes first. Let's see. So the percentage right now is being sorted. Okay? So the first one is the one that has the largest percentage. And when I do the sorting, I also keep the ID. So the ID right now is showing, okay, the number 4 chromosome has the greatest percentage. And this is the order. Okay? So the number 7th chromosome is the worst after this sort. Okay, now I'm gonna the sum of all the percentage, if you sum them up, it's gonna be 1, right? Because they are percentage. There are some percentage within 100%. The sum of them is 100%. So I'm going to randomly generate a number from 0 to 1, and you will decide which chromosome is being chosen. So let me see what is the best way to do that. Okay. So here I'm going to do this selection process. And it's going to be a while loop. So, is it? Maybe a for loop. For I equals to 1 to population. Okay? So every time you generate a random one, so random percentage, okay, equals to rand1, just a number. Once I randomly generate a number, I need to know where it is. So what happened was, I'll show you in the iPad. Okay. It's not happy. Maybe I don't show you on the iPad. The iPad is not happy. Okay. I cannot show you. Just do it on the Meta. Okay. So if I randomly generate, for example, if the number is 0.8, so it's gonna be a bunch of values being accumulated. So like I have 20 of 20%, right? And the largest one goes first. So they are values like, for example, 9, 9, 2, something like this. And the last one is 0. Now when I generate my random number, for example, is 0.3, then 0.3 probably is somewhere here. Because 0.3 minus this, minus these three numbers, you will have basically if 0.3 is like this large. So you are pointing at the fourth one. If you go from the first one, okay, the point. How do you say that? If there's a ruler, this is a 9.5% wide. This is a 9.2% wide. This is 8.9% wide. And if you randomly generate, okay, 0.3, so this random pointer is pointing at this particular one. So you just count, okay, the random pointer is pointing at which one? So if this one is being randomly chosen, okay, that one is chosen. So I'm going to do this 20 times. So if a chromosome has wider range, it has greater percentage to be chosen, right? So now the way to make it work inside MATLAB, you are going to minus the percentage one by one until your after the subtraction, the remainder is within a percentage. Then that particular ID is the one. So there's another for loop. So percentage, the ith one, and minus the random number, Oh, I should say, if the random number is smaller than or equals to the percentage of the ith one, then that particular one is the chromosome. So selected ID I is the ID I. So if the first one is the one, then that particular one is being chosen. But if it's not, that means you need to move on to the next one. That means you are moving on to the next one. You need a while loop. You need to keep on keep doing the subtraction. You need to minus. So you need a while loop. No. So you don't need this. I should say j equals to 1 here. If the random number is smaller than the j, which is j, then selected ith one equals to id the j. So if not, I need to keep on subtracting. So while directly say while outside. While while this is larger, then keep on subtracting. So random number equals to random number minus the percentage, and j plus 1 until your number is, the remainder is smaller than or equals to 2. So that particular one would be the selected IDR. So should be, yeah, I think this is right. Double check. Okay, so run the code. Now, the population is a sorted percentage. Now I randomly generate a value. The random percentage is 0.25, and it's larger than the ith percentage. So I need to subtract the jth percentage. I subtract the jth percentage, which is 0.077%. So after subtracting, the remainder will be 0.18. Okay, move on to the next one. Subtract again. So remainder is 10%. You need to subtract again. So now remainder is only 3%. And the j is already 3. So going to the fourth one. The j is 4. So the fourth ID is 16. So the 16th chromosome is selected. So by this process, because initially I random generate some number, like 25% or something, it's located right here. Because the sum of the 3 is less than 20 something, and then it will be pointed at here. So this one is being chosen. Okay, so if I keep on doing this, let's see what at the end. Let's take a look. All the selected chromosomes. Okay, I think it's done. Let's see. So if you take a look at selected ID, okay, and let's see if we have double selection. So 15 has been selected twice, 3 times. 15 has been selected 3 times. Huh. My OBS. Come on. I'm not sure if I lose the. Okay. I'm not sure if I lose the video earlier, but we have this one, right? I hope. Okay. Let me check. Computer crash. Yeah. I still have it. Okay, I just need to continue. Okay, so over here you can tell the 15th chromosome has been chosen 3 times. Let's see why. If we check on the sorted ID. Sorted ID. Actually the 15th one is this one. So how about number 1? Was it chosen multiple times? Number 1 only chosen once. So in this case, our best chromosome was not chosen enough. I should figure out a way to make my best one to be chosen more. So over here you can, so when you generate a pie, you want to generate greater percentage for the ones that has the better fitness, right? Now they are equally, based on the fitness, they are, the percentage is based on this fitness value. So if I have smaller one, I want, if I have greater value, I want its selection percentage to be greater. I think linear order may not be good. So I can actually play a trick. Right here, I can maybe allow this value to be double. So this D value is having a square relation with my fitness. So if you have greater fitness value, I give you square opportunity to be chosen. So if I do that, let's see what's gonna happen. Dr. Square. If I do that, my ID, okay, the best one is 20. Now let's take a look at the selected. $20 was chosen 1, 2, 3, 4, 5 times. This is the best one. So by doing so, I gave the best chromosome a much greater opportunity to be chosen. It was chosen 5 times. I think it's great because I like the one that has the best chromosome. Okay, so now I want to circle where those chromosomes are. Since I have 20 of them, but I don't know which one is now the overall best. So I will, after the sorting, I will show you which one is the overall best. So the value for the first one, that particular point will be circled by a different color. Let me try blue, greater marker size, maybe 8. What? Sorry. I didn't memorize them. So let me memorize them. So maybe K and I. K should be. So great. Here. Okay. So this particular one is the one with the best objective function value. If I try it once, I'll try it one more time. This one is the best. Let's see more. Okay. Really? I want to draw the quadratic objective function to just to double check. So let me plot out easy contour, and my objective function is x1 squared plus 10 times x2 squared plotting in the zone. Right? Let's take a look. Yeah. So this is how the objective function look like. So over here you can see it's this point is having the smallest objective function value. Let's generate again. See, this one is even is in a lower level than the other 2 points. If I try a different function, for example, if I try different coefficient 5 right here, if I do that, I need to my fitness, I need to make a change here. So 5 here. If I change the function form, okay, so this one is slowest. Okay, so from here you can tell, okay, you GA randomly generate some, evaluate the fitness of every one of them. This one is being found to have the best objective function value. Okay, and let's see how many times this one is being chosen. So the ID, this is the first ID, and selected ID. Number 1 is being selected 5 times. The first chromosome is being selected 5 times. Okay, which one is the worst? The 15th is the worst. There is no 15 being right here because the percentage of the last one being selected is 0. About number 2, the percentage of number 2 being selected is so low. Okay, 19, there's no 19.
这是我在网络上找到的 The Percent Show OK 相关结果。
I didn't call you. Number 7, no selection. Number 4, no. Number 3, no. Number 6, no. Number 11, no. 20, yes, 20. So 20 is the one that is ranking 12 in the original chromosome. Out of 20 is ranking 12. And that one is being chosen once. Okay? We still need some of the bad ones. Okay? So later on we are going to do the so-called crossover and mutation. Okay, so after this part, selection is done. Now we need to do crossover. Okay? So I can say for every we have 20 of them. So for every 2 out of the 20, we will decide whether we do crossover out of the 2. Okay? If we do that, we will have, because at the end, we still only need 20 of them. We don't want to generate more. So if I randomly select 2, they have done crossover. Those 2 parents will not do crossover with others anymore. So it's based on my decision. If I have 20 parents, they can cross over, they can change their body, but if I already select 2, okay, you guys are a couple, you're going to decide whether you exchange your body or not. Once I select these 2, then you will not do crossover with others. And this is my decision. So now, I need to decide the crossover pairs, which 2 performing crossover, the pairs. So I will give them will give them equal opportunity. So maybe 50%. Or what I can do is I can randomly generate 1 to 20 number values, and then they are values. No. I can. I just randomly generate 20 values, and then I will just sort those 20 values, and when I sort, the output I keep, so this is some dummy variable, but I need an ID, so now I'm going to call this ID2. Okay, what does this do? If I randomly sort 20 randomly generated values, the original index comes from 1 to 20, right? Now, since they are randomly generated, if I sort and keep the ID after sorting, then I will have a bunch of IDs, so ranging from 1 to 20, and they are basically randomly sorted. So I'm gonna say, okay, the first two, the third and the 11th, you do crossover, and the other second pair, fourth and the first one, you do crossover. Okay, 11, 10 and the 16th, you do crossover. So by this one line, I already decide which are the pairs to perform crossovers. Okay? So for 1 goes to 10 actually. Population divided by 2. Every 2 you perform a crossover, right? So every 2, that my first 2 chromosomes will be the third one and the 11th inside the inside the selected ID. So I need to know I have a list of selected ID. Then I need to know third one and 11th one represent which one. So the third one is 13, and then 11th one will be somewhere here. Okay. So the crossover ID would be the first every 2, right? Every 2. So ID 2, the I1, and I can from 2 to population. Yeah, this is easy. So I minus 1 and ID 2 I. Yeah. So these will be the 2 IDs to be selected. I will show you. No, population. So over here, the sorted ID, first 2, 19th and the 14th, will be chosen out of the selected chromosome. They will do crossover. So from here, 19th and 14th, from the selected ID, so 19th is out of this, will be 1. And the 14th will be, this is 12, this is 14. So over here, 14 and 19, is it? ID. No. 14 and 19 out of selected IDR. Out of selected ID. Do it again. So first two will be 2 and 20. 2 and 20. So it will be 3 and 9. So here 3 and 9. So deciding whether you do crossover. Okay, now the third and the ninth, you decide whether you do crossover. And you are going to do this single digit crossover. So you will be performing maybe a for loop, 1 to the 20. 20 is the number of our chromosome. Maybe just 19, because it doesn't make sense if you let's say this is a chromosome. This is the first digit. So I'm deciding, okay, this is my pointer. So this is my 20th. This is my 19th. So over here, okay, if we decide to do crossover at 19, then the tail swapped with others. So we only need to do this crossover decision at the middle of 2 IDs. Okay, so from first one to the one before the last digit. So from 1 to 19. So you will be generating a random number again. So if this random number is smaller than or equals to your crossover rate, that means you will perform crossover right at this position. So if that happens, the chromosome is my X, right? Chromosome is my X, and it's gonna be the ID will be here. First one. The 2 chromosomes that to swap their body will be these 2. But swapping at where? So over here at the ith position. So this is so I plus 1 to the tail. This will equals to the other body. The other body. Okay. Oops, sorry. The other chromosome's tail. Okay? But when you do that, the first chromosome's tail will be disappeared. It will be replaced by the other chromosome's body. So you need a memory. So you need a memory. I'm gonna call this 10. We're going to keep it right here inside 10. So the other body, the tail of the other chromosome will equals to 10. Okay? And whenever you jump into this area, you want to clear 10. Just delete whatever you did in the past. And whenever you perform crossover, you are going to break. So you will be out of the for loop. Let's see if that works. Let's pause right here. Okay. So right here we are the 15th and the second chromosome will be doing body swapping. So the random number I generated was smaller than the crossover rate. So over here, the temp would be, okay, something's wrong. Okay. No. Should be like this. Typo. Should be like this. 19. Okay. Do it again. Okay. So the temp would be some second half. Actually 19 of them. So at the first time we will, right at the first one, we decide to perform crossover. Okay, so crossover. After that, the break brings you to the outside of the for loop. Then moving on to the next crossover. Okay, and then you will perform the crossover. Earlier it was the 20th and the 6th. Now it's the 19th and 16th. So it will keep on doing this until you finish. Okay? So after you complete the crossover, you probably have no idea where they are. So let me try to plot out what would be the new position after you perform the crossover. So in order to do that, you need to check the value again. So now you will have a for loop from 1 to population. And you will be, actually what we can do is over here, we directly name those crux. So those would be the chromosomes after crossover. So before I do that, so I don't need to do the 10. Before I do that, I need to say this. No cross. Okay. So cross equals to the one before cross. So over here, the cross, the tail equal, here. Let me see if I'm right. The tail of the first one equals to the tail of the second one. The tail of the second one equals to the tail of the first one. Yeah. Then after break, all the X cross will be the new chromosome. So over here, I just need to make a drawing. So let me do a for loop. And then try to show you where are the positions at those cross, the chromosomes after the crossover. So here I'm gonna just say cross. Same way to compute. So plotting, same way of plotting, but plot out the one after crossover. here I'm gonna use a cross, maybe green color. Let's take a look. Okay, something's wrong. Okay. I should say, okay, I should say I minus 1 here, and I here. And here is I minus 1, and I. Okay. Crossover ID. Let me see. This one, yeah, this one is one of the chromosome. Why can't I do this? I equals, I misuse, I should use J right here. J goes from 1 to 19. So I misuse index. So here should be J plus 1, J plus 1. Let me try it again. Good. So from here you can see, if you zoom in, you can see we still have some points that are staying at the same position, like these ones. Maybe I change the color and make it larger. Marker size, I should make it 10. This one 10, and this one 5. I need a better color, so color, dark green would be 010, is it? No, dark green should be this. No, this is light green. So this. No, this is purple. Purple. So this. I'm gonna make it darker. Oh, very light. What's the color for dark green? This. Okay, I think it's better. Okay. So earlier at the beginning, we have red dots. They are randomly generated chromosomes, and we only keep the feasible ones. And now we use some kind of selection. So some of the good ones were chosen. And from those good ones, we ask them to change their body. So from here, you probably can tell maybe this green one came from this. Why? Because these two are having the same X1. I think they are, it looks like the X1 is the same. But their X2 changes. So that must happen, it must come from some chromosomes that we selected, and inside the body, some part is being changed. So that kind of swapping allows you to change value. And if you have 10 digits, and let's say, okay, these two was swapped. And you know, in binary, the tail contribute very little. That means if some value right here changes, I'm gonna, the X value is going to change just a little bit. But if someday you swap the first 2 digits, in binary, the first 2 digits represent a great jump. So digital jumping, digit swapping allows you sometimes change value by a little, sometimes change value by a lot. So from here you can already tell GA is able to find new positions out of this kind of random process. Okay. But from here you can tell some of the ones will jump into invisible space. What we can do is we don't kill them anymore, but we can give them a poor fitness value. Okay, so we still need to check their objective function. So for every maybe not yet, because we need to do mutation. So this part is just for you to know, okay, where they are. Now we perform mutation. Mutation is easier to program. So for we just directly mutate on top of the chromosomes that was being crossed over. So now we have basically X cross are the capital X cross are the chromosomes. For example, X cross are the chromosomes that has been crossed over. So now I'm going to go one by one, and you are going to again have a pointer. Now you can point from the first one to the last one. Okay. So if you generate a number that is smaller than or equals to your mutation rate, if that happens, that particular chromosome's digit will swap from 0 to 1 or 1 to 0. So that particular chromosome is right here, the I and J, right? So I'm gonna say if this equals to 0, then I will change it to 1. Otherwise, change it to 0. So that's mutation. So once it's mutated, I'm gonna do the same thing again, just to plot out where they are. But this time, I'm not going to use a cross. I'm going to use a square box and change a different color, maybe black color. Okay, let's have a look. Okay, a lot of mutation. Many mutation. Many? Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9 mutating. So from here you can tell, like this particular one. Actually, it mutated a little bit, changed a little bit, maybe just 1 digit. I worry my mutation rate is too high. So in this case, I may change it to maybe only 3%. So, like this particular one, exactly no mutation. Okay? I feel like my crossover rate is too high, so maybe 2%. Because my best one disappeared after crossover mutation. My best one disappeared. So I would like to have even lower crossover rate. Okay, I think this is better. This is better. Okay, because let me try again. Okay, we'll see. So now, red dots are the original ones. Circle is the overall best out of the red dot. Green cross are the crossover ones. Black square are the mutated ones. You don't want too many mutations. Okay? And overall, you can see the green cross and the black boxes are closer to the best solution area. Almost no sampling over here, because those red chromosomes up there were having bad fitness values. Maybe during the selection process, they didn't have a chance. They were not selected. And when we did the crossover mutation, the randomness didn't push us back there. But it's still possible. Okay? Anyway, now we need to check the fitness after we did the final fitness check. Okay? So how do we do it? We will do exactly what we did earlier. So for one, actually I can do it here. Final fitness check. Do it inside the loop over there. So first of all, you need to see if it's feasible. So you will plug into the objective function and see if it's feasible. If it's not, I'm going to just give a poor fitness score. So I'm gonna call this fitness final. If it's poor, if it's feasible, basically the objective function value is the fitness value. Else, when it's not feasible, I'm gonna give away a pretty poor number. Maybe I can just directly choose the largest one, the fit max. I just give it a max fitness value to that particular chromosome because it's gonna be a really bad one. So once I complete those, the overall best one will have the smallest fitness value. So over here, this is final and mean, right? And checking all. I will need to know which one. ID best. So overall, I'm gonna plot out the overall best. So overall best, just plot out the ID best. This time, maybe a even larger circle, red color, marker size 15, line width 2. Let's see. Marker ID best. Marker size and line width. Okay. So that large red circle is my overall best. So actually, if you observe, at the beginning we generate a red one, and that was the blue circle means it was the overall best. But out of crossover and mutation, it jumps to here, so that becomes the necessarily a worse one. So you can see crossover and mutation sometimes does not keep the best one. So you can play with the programming. You can maybe figure out a way. Maybe you don't cross over the best. You always keep the best, maybe. But since I have this code, I'm not going to change it. There are multiple strategies. Okay, so now this is the overall best. Still not too bad. So going back to the beginning, I need a super large while loop or for loop for k goes from 1 to generation. Okay, then so my k will evolve, but at the beginning, when k equals to 2, I need to keep the overall best. So so over here, I will say if k larger than 2, then the very first chromosome for that particular population equals to the best one from the past. The best one from the past would be this one. And best ID. Best ID. And you can say break here. So it doesn't perform whatever you're doing right here for random generation. Let me check if it's right. Okay, so run the code. So first time is the first population, the first generation, so you don't have overall best. You perform the whole thing again, whole thing over. You run the whole thing to complete the first generation. Oops. Line 59. What's my K already? Did I misuse K? Why is that? Try again. Okay. I don't know what happened. Okay. So in the next iteration, because no, k now equals to 2. So here should be k minus 1. Run the code again. Maybe we will do draw now right here. Okay, and maybe let's do a pause. So this is the result for first iteration. And then let's take a look at the other iteration. Because I use k comma I, k comma I. So every time I have k almost there, but some bug. Okay, fit. K K now equals to 2, yeah. By 2, perfect. K equals to 2. I think when I break, I didn't perform all these. I cannot say break. Because if I break, the for loop disappeared. So I should do this. If I do this, only the first one. I should say if I equals to 1, then do this. Otherwise, do the rest. Okay. If k is larger than 2 when I equals to 1, take the overall best from the previous, otherwise do whatever we did. Okay, should be correct now. No, why? Sorry. When k equals to 1, we still need to do this. So I should we always do this. Okay. And we're going to do this. So when k is larger than 2, for the first one, you will perform this. And you don't need to do this anymore. So you will, okay, you can say, but you want to do the plotting. Here, I should just, here, that's why. That's where I should do this. When, if k larger than 2, and if I equals to 1, then do this. Otherwise, do this. Yeah. I think this should be right. Please. Okay. Next. Okay. So from here, okay, a lot of dots. I need to turn off the dots, otherwise there are too many. Okay. So you can now already see it's evolving, but now we have too many dots. I'm turning off the red dot. And overall best, I think we keep it. After crossover, I think we don't draw it anymore. After mutation, we don't draw it anymore. Okay, that's good. So blue is the overall best from the beginning. The red is the overall best out of crossover and mutation. Now let's take a look at next iteration. Third iteration. So somehow we lose the overall best. The way I program, I didn't keep the overall best well enough. The crossover mutation killed my overall best. So maybe I need to do something with the crossover mutation. But at least you can see it's keep on trying to find good solutions near the physical space. And I'm sorry, my coding keep on having issues. But from here you can tell it's the randomness of GA allows you to move around. The goal is to help you understand why GA can perform optimization without doing derivatives. Basically, it's a bunch of randomness. And let's get back to everything I said at the beginning. We have 20 chromosomes, 20 digits for the chromosome. So basically, the possible solution set is 2 to the power of 20. 1 million possible solutions. But by this random process, you can already see only several iterations. I only performed 14. And you can see GA is trying to find solution near the area that could have the optimum. And this is only 20 trials per iteration, and we have done only 14 iterations. So 280 trials out of 1 million. So you can imagine if I correct some of the bugs in the code and then do not allow crossover and mutation to delete my overall best, I should be able to improve all the time. Crossover and mutation will help me to find newer points, but always keep the overall best. So only if I have another overall best out of the crossover and mutation, then I upgrade my overall best to the new one. So if that's it, if I can spend 30 more minutes, probably I can program it more effectively. So I'm keeping the overall best and allowing crossover and mutation to jump around. So I should be able to find the overall optimal, maybe somewhere here. Okay? So that's the spirit of evolutionary design optimization. And if you Google evolutionary optimization, if you Google this, there's even a Wikipedia of this. And if you go in, you will see there should be a list of over here. Ant colony, artificial bee colony, bees. You can see mathematicians try to use how nature behaves in mathematical problems. They try to follow how ants trying to explore the space. and particle swarm, firefly. I remember some of you used some of the fly algorithm, right? Do we have GA here? Oh, here's a list on the right hand side. Every one on the right hand side is a optimization problem, GA. Okay, GA itself has a general category because GA probably is the most popular method in evolutionary algorithm. And now, after today's lecture, I hope you get to understand what is chromosome, crossover, mutation, and some other like selection and so on. You now probably can understand better how those evolutionary algorithms finds optimal solutions. Basically, it's based on some kind of random process, allowing the best to find even better ones. Okay, so that's the lecture for today. I'm sorry I could not generate 100% correct GA code today. There are some bugs. I need some time to check. So after today, I will go back and check where did I make inappropriate coding, and also I will upgrade the way I treat the crossover ones and the mutation ones. And I hope maybe later I can send you this one for your reference, so maybe you can use it to do your own research. Okay, so that's it for today. Any questions? Okay, I hope this is helpful. Okay, that's it. That's it for today.